Okay, I want to start really quick with a question type that shows up in 2.4 that I didn't really talk about. You have the information to, but I don't think a lot of people connect it in their brains until they see an example of it. So I wanted to do an example of it. So say we were given this information about a function, and this is all the information. Oh, and I forgot to actually write what the question is going to ask. Nope. Let's choose the best estimate for F8. And we'll do crap. What was it? It was 18, 15, and 20. So say the only information we're given about a function is that f of 4 is 6, f prime of 4 is 3, and that the second derivative is positive everywhere, and we want to choose a best estimate for f of 8 out of 15, 18, and 21. So how we're going to do this is the first thing we're going to look at is we kind of know a way to approximate f of 8 from 2, 3, where we use that idea of the tangent line approximation, where we take f of 4 and then we add on a certain amount of derivative values. And since the difference between 4 and 8 is also 4, we would multiply that derivative value by 4. So we'd be able to estimate that the value would be approximately around 18. So that you may want to pick 18, but that's actually not going to be the best estimate because of the fact that we have, let me reshare it then. That work, Shannon? Cool, you're welcome. So you might want to choose 18, but that's actually not going to be the best estimate because we now have this kind of extra piece of information where we know that the second derivative is positive everywhere. Oh, there we go. So if we think about what this estimate that I just calculated is doing, it's essentially saying, well, if here's x equals 4 and over here is x equals 8, then what I'm technically doing is I'm technically using the tangent line to approximate f of 8 being approximately 18. And f of 4 would be down here. So remember, using this is technically using that tangent line. That's why it's called a tangent line approximation. But since we know that the second derivative is positive everywhere, we know that this graph is concave up. So if this graph is concave up and I'm increasing, which I must be increasing because my derivative is positive, if I go from 6 to 18, I must have increased. So if I have an increasing concave up function, I don't know exactly what it looks like, but it's probably going to look something like this. Like that thing that I just drew is increasing in concave up. So because of the fact that I know it's concave up, I know that the function has to bend upwards, so I should actually recognize that the estimation from the tangent line is actually being too small. So estimate might not be exact right answer, but it's a better estimate, would actually be to choose 21, because the fact that it's concave up tells me the actual value of the function is going to be somewhere higher than this tangent line approximation is giving me. Say instead that the second derivative was negative everywhere, then we'd have concave down. Well, if you're increasing in concave down, you must look something like this. Once it catches up with me, there we go. So if we're concave down, if we were to have been concave down, then the fact that it curves downward tells me that the estimation from the tangent line is actually too large. So if the second derivative had been negative, the actual answer would have been 15 because we know that the estimate should be less than the tangent line approximation. So I'll just keep both of those up because they're color coded. But essentially, so we now have this kind of extra piece of information of the second derivative to kind of tell us whether or not our tangent line approximation is too large or too small. So that's a type of question that you'll see on your homework. So now you've seen one, so hopefully you can get that one done. Questions on that before we finish 2.5? All right. Savvy. All right, so 2.5. Started the other day, but got barely anywhere because technology hated me. So reminder, we're talking about marginal cost and revenue and profit. So the way we're finding that is we're using the idea of the slope. And then we went through this first example, which actually had nothing to do with slopes, but just had to do with regular profit in general. But anyway, so now let's say, for instance, you work for a company and they sell mattresses. And they are asking you to decide whether or not they should increase the number of mattresses they sell. Say this is some magical company that will sell absolutely every mattress they make. So say right now they're making and selling 100 mattresses and they want to know, well, what if we should make the 100? What if we should make another mattress to sell? What if we should sell 101 mattresses? So what would we have to consider to figure out whether or not that would be an actually good move? So if you think about it, in the back of your mind, you might be thinking, well, selling more things would mean more profit, right? Well, not necessarily, because say you have some weird cost and revenue function such that at this point in time, making that next item would cost you more than the revenue you would make from it. So then your actual profit would be going down. So what we would need to make sure would happen to make sure that they should actually do that and it would make sense is we'd want, I need to actually have a pen on. That would be a good idea. So you'd want to make more profit. You want to make sure that selling that next extra item would actually make you more money than you were making before. Because when it comes to cost revenue functions that are not linear, super weird things can happen. So I'm going to come back to this really quick, but I got to get some notation down first to be able to write what I want to write. So some notation. So if I ever want to refer to marginal cost, well, Wiley will often refer to it as MC, but I'll usually refer to it as the derivative of cost because that's what it is. Marginal revenue can be referred to as MR, but it is the derivative of revenue, which is the more important piece to remember. And then marginal profit, so let me kind of leave a space really quick. So remember, profit function is written as pi of Q. Now you could technically write MP. That's not going to be used as often as MC and MR. Marginal cost and marginal revenue are pretty often, especially on Wiley, referred to as MC and MR. You won't really see MP very often. They'll probably just say the words marginal profit, or they might refer to it as the derivative value. One thing that's really important about marginal profit, that is equal to the marginal revenue minus the marginal cost. You know, this kind of mirrors the fact that profit equals revenue minus cost. That kind of pattern follows over to the derivatives. So the derivative of profit is equal to the derivative of revenue minus the derivative of cost. So if I pop back up to this idea we were just talking about, so if we wanted to make sure we were making more profit than we were before, what we would want to look at is we'd want to look at whether or not the marginal profit was positive. Because that'll tell us if we make one more item, how much more or less profit we'll be making. So I've said this kind of idea multiple times, and again, you want to make sure this connection is in your head. A derivative is a slope. So if we want to talk about making the next item, if you think about a derivative as a slope and you think about slopes in that step way, we have the rate way, but if you look at the kind of step interpretation way, that tells us if we increase the quantity by 1, how much our profit is going to increase or decrease by. So that's exactly what we'll want to look at. We'll want to look at our marginal profit and see whether it's positive. But in that case, that would be equivalent to saying that the marginal revenue minus the marginal cost is greater than 0. Because I'm saying down here that that's equivalent to the marginal profit. Which would also be equivalent to saying that the marginal revenue is greater than the marginal cost. So we kind of have these two different ways we can think about it. Sometimes we're going to need to use one over the other. Say we're only given cost and revenue, then we really need to look at revenue versus cost as opposed to finding the profit function. Especially, we'll see some examples in a second where we're just given the graphs and we're not given the equations, so we can't find the profit function. So we would need to use the relationship between R prime and C prime. Okay. So now approximately down at the very bottom, let me scroll down a tiny bit. Maybe too far. Approximately marginal cost or revenue or profit, to change the symbols. Marginal cost would be approximately equal to C of Q plus 1 minus C of Q. Whoa. Zoom back out. Zoom. Now this is just a general note. We will use techniques to estimate C prime of Q or C prime of A for some value. So while it's kind of good to note this idea that the marginal cost is approximately equal to the cost of producing one more minus the cost of producing the original amount, but I don't want you to think that that's then how you should go about finding it. We have these techniques already for estimating a derivative value. We use the average rate of change. So we still want to use those ideas. And next week we'll actually come into, we'll look at our derivative rules finally so we can find them officially. And we'll use that starting next week. So it's kind of just a kind of side note that that's approximately what the marginal cost would be equal to. But you shouldn't really be using that to find the value, really. So anyway, I'll leave that up for a couple more seconds in case people haven't gotten it down yet. And then I'm gonna look at something really quick while I do that. Oh goodness, stop it. Okay, never mind. All right, moving on. And I should have drawn this before I printed these notes, but I forgot. So we kind of need to specify because that graph doesn't show us much at all. But so say we have these two functions, C of Q and R of Q, so we have our cost and revenue functions, and we're kind of back to that idea of that mattress company that wants to know whether they should sell more mattresses. So they want to know, should the company make the 101st mattress? So I've noted where quantity 100 would be. And now, so we don't know what the actual values are. We don't know what these functions are. We don't know their equations at all. But we're still going to be figure out whether it would be wise for them to make this next item based off of that kind of relationship. So we found out that we want the marginal revenue to be greater than the marginal cost. Well, here we just have regular cost and regular revenue. But again, derivatives are slopes. So let's look at the slope of each one of these functions kind of around that point, Q equals 100, and I'll talk about why it's 100 in a second if you're not sure why I'm using 100 and not 101. So if I kind of find these two tangent line kind of ideas here, and I look at those two little line segments that I've drawn, and I want to figure out which one's steeper than the other. Well, the black one, the top one, is steeper than the red one. So that one came from our revenue function. So essentially, since the slope of R of Q, R, is greater than the slope of C of Q, R prime of Q is greater than C prime of Q. So they should make the 101st mattress. I'll put in parentheses because they make more money. That's E and the Y kind of blended together. They make more money. And we know that they make more money because essentially we've just found I don't want to say a roundabout way, but in a kind of side note way, not even that, an equivalent way to finding that the marginal profit was positive. So if the marginal profit is positive, that means that they're making more money than they did before, so it would make sense for them to make that extra mattress. Excuse me. So if you're wondering why I'm using 100, not 101, here's the reason. So the things that we're looking at are the slopes. So remember, if we want to look at slopes, if I want to know about making the 101st thing, I actually want to look at the slope at 100. Because again, if you think about the slope in the step way tells us that if we increase the x value by 1, so essentially in this context, we're increasing the amount of items by 1, and that value will tell us how much more profit, revenue, or cost we'll have to deal with. So we want to look at the amount of profit we will gain or lose from making the 101st. So we want to look at the slope at 100 because the slope would tell us one more. So hopefully that makes sense. Questions and concerns on that one before we do a slightly similar one? And I don't think we're going to take all of class today because once we finish this, I don't really want to move forward because all my other classes are in the same file. Anyway, I'll ramble about that at the end. All right, this one then. So we've got a graph of just the cost function, regular old cost function. Again, we only have the graph. We have a couple of values here, but they're not really going to be that helpful. And we don't have an equation. So we're still kind of in this similar situation of not having a ton to go off of. But we want to know, does it cost more to produce the 500th item or the 2000th item? So some notes about like verbiage. Note the difference between saying something like the 500th item. Oh my goodness. Versus saying 500 items. Oh, what is happening? So if it's talking kind of like about a very specific item, you can pretty much guarantee that they're talking about the derivative, if that wasn't already clear from the other bits of context of the question. Whereas if it's kind of a group of items, a set of items, that's probably talking about the just plain old regular function. So there will be some context you kind of need to read correctly to figure out whether you're talking about regular cost or marginal cost. But in this case, since we're talking about very specific items, we want to talk about the marginal cost. Now, note that the Q values on the Q axis are in thousands. So the 500th is actually going to be around 0.5, and then the 2000th will be around 2. Now, as I said in the last example, you want to look at the one before it. Now, in this case, it's a little wonky because of the fact that this is given in thousands. So say I look at the 2000th item. So the 2000th item would be right here. If I want to look at the one before it, I don't go back to 1 because that would be a difference of 1,000 to 2,000, which is not a difference of just one item. So we'd essentially want to look at the slope kind of just directly behind this. It's almost like you're exactly at 2, but you know, just kind of that generic, very, very obnoxiously close to 2, but not quite there yet. And that's specifically because of the fact that this Q-axis is in thousands. If this Q-axis was in just ones and we were looking at the first and the second item, sorry, if we were looking at the second item, then we would jump back to Q equals 1. But since we're talking about thousands, it's a bit different here. So if I draw kind of a very bad tangent line here, you'd be looking at that for the 2000th item. And the 500th, so 500th would be, you know, well, we're looking at the 499th, but it's approximately right around there. And we're looking at the tangent line of that. Well, between those two tangent lines, which one is steeper? The one on the left. The one around the 500th item instead of the 2000th item. So since the slope at well, I tried to make it at 499, but you know, the slope of making, I'm going to say 502,000 just for my sanity. So the slope at 500 is steeper than the slope at 2. So we would say it costs more to produce the 500th item. And I'll put tangent line is steeper to remind us why. Let me change colors so I don't have too many of the same color line floating around here. What about the cost to produce 3,000th versus the 40,000th? 4,000th. So again, I'm going not quite at 3, but you know, if you went at 3 just for your sanity, it would be okay. And around 4. Which one of those two lines is steeper? The right, the one associated with the 4,000th item, so it would cost more to produce the 4,000th item than the 3,000th item. Okay, concerns on that? Cool. So that's actually the end of 2.5. There is one last thing I want to do because I'm scanning through your homework just to make sure that there's no kind of last minute things.
You go over number 1 again.
Yeah. This one right here?
Yeah.
Yeah. So 500th item, since this is in thousands, is going to be over at the 0.5 point. So if I go over to 0.5 and I kind of draw my little tangent line, and then I go over to 2 and I draw my tangent line approximately there. Technically we want 1.999 because we want to look at the one directly before it. But now between those two lines, you know, I got one that kind of looks like this versus one that kind of looks like this. Which one of those lines is steeper? This one would be steeper than this guy. So whenever you want to look for which one is costing more to produce, you want to look at the slopes. So because we're looking at C prime instead of just regular old C. So since the slope of the line at 0.5 is steeper than the slope of the line at 2, it would cost more to produce 100th because the tangent line is steeper there. Does that make sense?
Yeah, perfect sense. Thank you.
Cool. Any other questions about that? So I'm flipping through your homework because sometimes I forget what problems I put on your homework and then I forget there's things that I technically have talked about, but you might not realize that we've talked about. Dun, 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 dun. Oh, there's that one. I want to talk about that one. Okay, cool. All right, let me jump over here then really quick. And we'll still probably be out a little bit early because, again, I don't really want you guys to getting too far ahead of my other classes. And we're about to start a new chapter, so we'll just start that on Monday. One thing to note, it's not really new. I just want to make sure that you're thinking of it when you're doing your homework. There's some questions where you're like given Q, that's not a Q, like C of 10 and a C prime of 10, and you want to estimate C of 20. That's just that tangent line approximation idea. There's no new thing from 2.5 that you need for that. It's just using it in terms of marginal profit
oh God.
verbiage. Is that a question or just an accidental unmute?
Okay, Lizzie.
I think it's an accidental unmute. Okay. So let me look at this one really quick. Same thing. Okay, cool. So there is one that I want to talk about though. So say, maybe I'm not going to phrase this in the best way, but say we have something like the revenue from selling 99 items is 150. And the revenue from selling 101 items is, I don't know, 220. Estimate the marginal revenue for 100 items. So note that we're just given the regular revenue, but we're asked about the marginal revenue. So essentially what's happening here is it's kind of like those table examples we did back in 2.1, but just the tiniest bit different, so I should talk about it. So we have 99, 101, and we technically want to talk about 100. So we know that the revenue at 99 was 150, the revenue at 101 was 220. We technically don't know the revenue at 100. So usually what we did in 2.1 when we had this table and we wanted to estimate essentially an instantaneous rate of change, which is essentially what we want here because we want a derivative value. So since we want a derivative value, we want to try to use an instantaneous rate of change, but we don't really have that idea here because remember we would take them on kind of both sides and then average the two together. But I can't take the average rate of change on both sides because I don't know what it is at 100. What we can do instead, though, is because we still know kind of what it is on either side, what we'll do instead is we'll be able to estimate this derivative value by taking the average rate of change of essentially just those two numbers that we know on either side. So we'll just take the average rate of change between those values that we know. So what is that? 220 minus 150 is 70 divided by 2, which is 35. Yes. So even though we don't know the actual revenue at 100, we can still estimate the marginal one because we know the revenues on either side. So we couldn't do that idea of finding both of them and averaging the two, but this is kind of the next best thing, which actually usually comes out to being equivalent. But anyway, so we would just estimate using essentially the only things that we have to do so. So that type of problem pops up on your homework as well. Everything else from 2.4 and 2.5, you should be able to do. Those were like the only two weird ones, I think. There's a lot more on here that have to do with just generic numbers instead of graphs, so it is slightly different than what we did earlier, but it's the same idea where the marginal cost is just going to be the slope. And it's a lot of using, again, kind of this past idea of estimating other values from an original and a derivative. So we're 10 minutes early, but as I said already, all my other classes are kind of in the same spot. So I don't quite think I want to take the time to move on to our next chapter yet. But on Monday, we'll be moving on to chapter 3, which is derivative rules. Oh, my little tiny screen froze. Oh well. Which is derivative rules, which are really nice because that's going to allow us to finally find these values exactly, and we're no longer going to have to just take estimates and our best guess. So we're actually going to be able to find them fully. So that's what we will be doing next week. I think that, yeah, that's all I got. So a little bit early today. If you have any questions, feel free to stick around. Otherwise, have a great weekend, and I will see you on Monday. Yeah. Stop recording now.